Welcome to chapter 15, where we are going to be talking about the concept of multiple integrals. So, we have seen in the previous chapters how derivatives get taken for functions of multiple variables. We have the partial derivative. If we want to take an integral of a function of multiple variables, we are going to need multiple integrals. So we're going to start off here in section 15.1, looking at the concept of double integrals over rectangles. So first, we want to recall how we defined a definite integral for functions of a single variable. So we can kind of see the transition here from 2D into 3D. We can see the similarities in these processes. So back when we were finding a definite integral from a to b under some function here, we would start by dividing AB into n subintervals with length delta x sub I. So we cut it into all of these smaller pieces. Okay? Each one of these has a width of delta x sub I, and we would choose a sample point within each subinterval. Typically, the sample points that are chosen are usually either like the left-hand endpoints, the right-hand endpoints, or the midpoints. Those are like the left-hand and right-hand rectangular approximations that you see in Calc 1. This allows us to form the Riemann sum with I going from 1 to n of f of x sub I star, that's the sample point, times delta x sub I. So we have, this is the width of the rectangle. This is the height of the rectangle at the chosen sample point. Again, usually like a left-hand endpoint or a right-hand endpoint. So this total value would be the area of one of these rectangles. And then the sum, the Riemann sum, tells us to then add up the area of all of the rectangles. And that'll give us approximately the area under the curve. Right? Now, it's not necessarily exact in this form because we would have to consider the fact that there's some empty gaps, there's some over approximations. It's not exact. The way that we make it exact is by taking the limit. So we take the limit as the largest of the lengths approaches 0. So all of these lengths right here, as those lengths start shrinking, so the rectangles are getting smaller and smaller and smaller, this approximate area gets closer and closer and closer to the exact area under the curve, and that is how we defined the definite integral. We had the integral from a to b of f of x dx is equal to the limit as the maximum delta x sub I approaches 0, so again, as the rectangles shrink infinitely small, and then we add up that area. That's going to give us exactly area under the curve. We're going to take this same argument and apply it to functions of two variables. So consider a function of two variables defined on a closed rectangle. So R, we would have dimensions going from A to B on the x-axis, and then C to D on the y-axis. So if we want to put this in set notation, this would be all ordered pairs xy that are elements of R2 such that x is between A and B and y is between C and D. So we'll kind of start talking about the diagram over here. You can see the rectangle R down here in the xy plane with x going from A to B and y going from C to D. So that defines this region, R. And first suppose that the function is greater than or equal to 0. So we're taking functions above the xy plane right now. Let S be the solid that lies above R and under the graph of f. So you can see all of this space in here between the function and the rectangle. So all of this in here, all of that is S. Okay, so all this space in here is S. That's the solid. So in, again, set notation, that's going to be all the points x, y, z in R3, such that z is between 0 and f, and x, y, those input elements are in R2. So S is the solid that lies under the function but above this rectangle. Our goal with the concept of a double integral is to find the volume of S. So again, in Calc 1, we were looking for area under a curve. In Calc 3, we're looking for volume under a surface. Okay, so volume under a surface like this, but above a region R. Now, the way that this gets broken up with like the rectangular approximations and stuff like that, it's a little more messy looking. So I'm going to pull up the graph on the next page, but then we're going to talk about it. So we're going to partition R into sub-rectangles. So the sub-rectangles, we will have x sub I minus 1 to x sub I by y j minus 1 to y sub j. So instead of taking just x now into subdivisions, we're subdividing x's and y's. And delta x sub I is just whatever that difference is between them. So the distance, right, from one value to the next. Same thing for the y's. We get y sub j minus y sub j minus 1. And the area of one of these little sub-rectangles is going to be delta a sub ij, which is delta xi delta yj. So again, now we'll look at the graph, but there's going to be a lot going on here. So we've got the rectangular region. So like this whole thing was R. So that was this right here. And we've cut the X into smaller pieces right here. We've cut the Y into smaller pieces right here. You can see delta X sub, it should be I, and delta Y sub J right there. And if we want to find the area of one of these sub-rectangles, so this is like R sub ij, right? We get delta x sub I times delta y sub j, so that's length times width, or base times height, whatever, to get the area of one of these sub-rectangles. Once we have that, we're going to choose a sample point. So remember back in Calc 1, this was like a left-hand or right-hand endpoint. In Calc 3, we're working in the second dimension here, so you don't have to just pick like a quote-unquote left or right endpoint. It could be anything inside the rectangle. So we're going to choose our sample point. That's x ij star, yij star. Then we can approximate the part of S that lies above each of those subrectangles. And actually, there should be a little piece added in here. Gotta fix that. So we're going to approximate the part of S that lies above the subrectangle using a thin rectangular box with base R sub ij and height f of xij star yij star. So we have the area of the base down here. That's the delta xi, delta yj times each other. We pick a sample point, so you can see I've got that in red right here. We pick a sample point, and that is the point we're going to use to calculate the height of the 3D object. So if we went back to like this one, we've got our little box here. We pick a sample point. We're going to use that to get the height. And we're going to draw this thin rectangular box and find the volume of that. Okay. And then we're going to do it again, and then again, and again, and again, and again for a bunch of different little boxes around here. And that's going to give us our approximate volume. So the volume of this box is f of xij star yij star. So that's the height times the area of the base, which is delta A sub ij. So again, height times area of the base. This is volume. So that's the volume for one box. If we do this for all the rectangles, so for all of these, and you can see I've got sample points, little sample points all over the place here, right? One for every sub-rectangle. It doesn't matter where they are. They can be in the middle, can be along the edge, in a corner, whatever. If we do this for all the rectangles and add the volumes of the corresponding boxes, we get an approximation to the volume of S. So we say the volume V is approximately equal to Riemann sum with I going from 1 to M, and a second Riemann sum with J going from 1 to N. So before we had one Riemann sum because there was only one variable. Now we have two variables, so two sums of f of xij star yij star times delta aij. So again, this is the volume of one of these boxes. And then when we add up all of the x's and y's, right, all of the i's and the j's count up, that adds up, right, the 1, 1 box, the 2, 1 box, the 3, 1 box, the 1, 2 box, the 1, 3 box. So it's just adding up the volume above every single box in this rectangle. That would give us the approximate volume. Now, we don't want just the approximate volume, we want the exact volume. So we take the same idea, the same concept as we did in Calc 1, and we make our subrectangles smaller and smaller, and that allows our approximation to get better and better. So as we shrink the rectangles, so the delta x sub I is shrinking to make this dimension shorter. Delta y sub j is shrinking to make this dimension shorter. We're going to make smaller and smaller boxes. And that's going to get us more accuracy in our volume until we let the boxes shrink basically to nothing. So the maximum of delta x sub I, delta y sub j goes to 0 of the volume. this is going to give us exactly the volume as we take the limit. And so this is how we will define the double integral. So the double integral, here's the notation for it. So you see we've got two integral symbols over r for now of f of xy dA here. So with respect to area, that's like x and y, of that same limit of the Riemann sum. So this is our precise kind of formal definition of the double integral. Now, if this limit exists, so if we are able to actually calculate the limit of this double Riemann sum, if we are able to integrate, then this function is said to be integrable, able to integrate. So if this limit exists, the function is integrable. If f is integrable, we can choose the partitions to be regular. So in other words, all of the rectangles that we drew, the delta x's, the delta y's, all that stuff back up here, they did not have to be the same size as each other. They could all be different sizes. But if we know that this limit exists, we can choose to have the same dimensions and area. So delta A will be equal to delta x times delta y. So no more A sub ij here, because we had to put the ij to indicate it was the area of that one specific rectangle. But now they can all be the same. So as long as this limit exists, all the rectangles can be the same size, which is great for us because it makes it consistent, and that makes it easier to work with. So we can let m and n go to infinity. So again, that's the number of rectangles is growing infinitely large as they shrink. Choose the sample point to be the upper right-hand corner of r sub ij. So if we go back up here, that's this one that I have right here. That's the upper right-hand corner. So we would just pick the upper right-hand corner, for example, in all of these. So now the rectangles will all be the same size. They will all have consistent locations of their sample points. And so we're able to kind of standardize this process a lot more easily. That's going to adjust our formula. So now we have double integral over r of f of xy dA is the limit as m and n go to infinity of the double Riemann sum of the function x sub I and y sub j delta A. So we can get rid of all of this additional like notation here and the star notation because we're settling on one specific point, not just an arbitrary point. And then delta A will be the same for all the rectangles, not changing from problem to problem or from rectangle to rectangle. So when it comes to the double integral, what is that telling us? The double integral is giving us this volume. So volume is going to be the double integral over r of f of xy dA. So this is the volume of the solid, which is f of xy, which is greater than or equal to 0, that lies above r and below the surface f. So let's take a look at an example. And we're not going to spend, more time than we need to on Riemann sums and approximations like this, because we want to get into more of the calculus of it all. But just we're going to try one out, see what this would look like in practice. Estimate the volume of the solid that lies above the square with x going from 0 to 2 and y going from 0 to 2, and below the elliptic paraboloid, z equals 16 minus x squared minus 2y squared. Divide r into 4 equal squares and choose the sample point to be the upper right corner of each square, r sub ij. So you can see I already have it kind of broken down here. We've got the square, x going from 0 to 2, y going from 0 to 2. I've broken it into 4 equal squares, and I've chosen the upper right-hand corner as the sample point for all of those. Okay, and I've labeled each one. what we're going to be doing, you can see in the diagram right here, we're trying to find the volume under this surface up here that's outlined in blue. We're going to find the volume above each of these rectangles, okay, or squares, using the height at the sample point. So you can see here, here's the 1, 1, here's the 2, 1, the 1, 2, and the 2, 2. So we use those sample points to determine height. We get the volume of all 4 of these boxes, add them together. That will be approximately equal to the volume under the surface. So we're going to get volume is approximately equal to double Riemann sum of f of xi yj delta A. Okay. In this case, for all our sample points, x is going from 1 to 2, and y is going from 1 to 2. So we're going to have I from 1 to 2 and j from 1 to 2. So we're going to go x sub 1, y sub 1, so that's going to be f of 1, 1 delta A plus, because this is a sum, f of 1, 2 delta A plus f of 2, 1 delta A plus f of 2, 2 delta A. So we need to find the heights of each of these rectangular boxes, and the area of the base will be the same for each of them because we're allowed to make them regular here. The area of each one of these bases, this is a 1 by 1 square, so the area is just 1. So when we're calculating the height, we just plug these values back into the function. So that's 16 minus 1 minus 2, so that's 13 times the area of 1. F of 1, 2, that's 16 minus 1 minus 8, so that's 7 times 1. F of 2, 1, we get 16 minus 4 minus 2, so that's 10 times 1. And then at 2, 2, we get 4 times 1. And we add up all of those values, we end up getting 34. So the volume of these 4 rectangles, these boxes combined, is 34. And we're using that to approximate the area underneath this surface up here. Now, is this exact? No, by no means. You can even just see from my little crude drawing here that there's a bunch of open space up here. So this is most definitely an underestimate, okay, an under approximation. We're going to look a little bit later at this example again and see if we can find the actual volume once we start using integration techniques. But for now, this is the approximation we have. It would be better if we made more rectangles. If we let m and n climb up infinitely large, right? If we said instead of just doing this for 4 rectangles, we're going to do it for 8 rectangles, or we're going to do it for 10 or 100 rectangles, all fitting in this tiny little region, you're going to get a much more complete picture of volume the more rectangles we use. But like I said a little bit ago, we're not here just to approximate. We're here to get some exact values and do some integrals. So let's talk about the concept of an iterated integral. So suppose f is a function of 2 variables that is continuous on the rectangle R. We use the integral from c to d of f of xy dy to mean x is held fixed, and f of xy is integrated with respect to y from y equals c to y equals d. So what we have here is a function of x and y being integrated with respect to y. So we're going to hold x fixed. In other words, we're going to treat it as if it was constant, and then integrate with respect to y. Now, once we are done with that, the result that we will have evaluated all of the y's, right, between c and d, but we will not have evaluated any x's. So the final result will give us something that depends on x. So this defines a function, and that's a of x is the integral from c to d of f of xy dy. So again, because by integrating with respect to y, we will have evaluated it, so all the y's will go away in this function. They will all disappear, be replaced by numerical values, but the x's will still be there. So what we have done here, this idea of holding one variable fixed or constant and working with the other one, is just like the concept of partial derivatives. And so this is known as partial integration. With partial integration, we can handle our multivariable functions one variable at a time. So we're going to now integrate this function with respect to x from a to b. So we have the integral from a to b of a of x dx. So this is the same thing as integral from a to b of that integral from c to d of f of xy dy dx. Okay, right, because a of x is just this, right? That's what this said back up here. So we take the partial integral with respect to y first, and then once that's done, we only have x's left, so we can just do a regular single variable, single integral with respect to x. Notationally, we understand that this integral is inside of this one, so we'll often just drop the brackets. So we'll get the double integral symbol here of f of xy dy dx, with y going from c to d and x going from a to b. And this is called an iterated integral. So we've got our dy dx with x and y both going between their own respective bounds. Now, this is what happens when we deal with y first, but we can also deal with x first. So similarly, if we take the iterated integral of f of xy dx dy with x going from a to b, y going from c to d, this would be the equivalent of just basically doing this backwards. So taking the integral with respect to x first, and then with respect to y. So we integrate first with respect to x, holding y fixed from a to b, and then integrate the resulting function of y with respect to y from c to d. So for these iterated integrals, we're always working inside out. So we always start with the innermost integral and then work our way out to the outermost integral. So what this means for our calculations of integrals is that the techniques of integration, the concept of antiderivatives, is not going away. Just like with partial derivatives, it doesn't change how we take a derivative. It just adjusts the process a little bit. It adds that little bit of an extra step of treating a variable like a constant. It's the same idea with double integrals. We're not changing how we integrate. We're just doing more of it and treating variables like constants as we're going. So let's take a look at some examples. So evaluate the following iterated integrals. So this one, you can see we've got the double integral of x squared y dy dx, with y going from 1 to 2, x going from 0 to 3. So if I go ahead and just kind of break this up a little bit so we can get a really clear idea of the division here. We've got dy going from 1 to 2, and then x going from 0 to 3, like this. So we're going to evaluate this inside integral first. So I'll go ahead and do this kind of, so side work over here. So I'll evaluate this integral first. So we need to take an antiderivative of x squared y with respect to y. So y is the variable, x is the constant. So the x squared is just going to tag along because constant multiples don't impact derivatives or integrals. Antiderivative of y is going to be 1/2 y squared, right? Or y squared over 2 if you like. But we're going to get, so that's 1/2, the x squared tags along, x squared y squared, like that. And then we're going to evaluate it from 1 to 2. Be very careful with this evaluation because we're only evaluating with respect to y right now. So the 1 and the 2 only go into the y. The x's will just remain x's. So we're going to get 1/2 x squared times 2 squared minus 1/2 x squared times 1 squared. So we get, that's 4 over 2, so that's 2x squared minus 1/2 x squared. So that's 3/2 x squared. So this is the evaluation of that inside integral. So we'll go ahead and just replace it. So we still have the integral from 0 to 3. We haven't touched that one yet, of 3/2 x squared dx. So now we have just a standard single variable Calc 1 integral. And you're going to see that this is the case with all of these multiple integral problems. We're basically just adding one extra layer to the problems. Once you get down to a single integral, this becomes a Calc 1 problem. So this one, take the antiderivative, that's 1/2 x cubed from 0 to 3, which, that's 3 cubed is 27 over 2. So the value of this double integral, this iterated integral, is 27 over 2. For the next one down here, notice same integrand, same value inside, but instead of dy dx, we have dx dy. And we have, so x going from 0 to 3, y going from 1 to 2, just like up here, but we've switched the order of them. So for this one, I'm not going to go through the solution to this one, but I would encourage you, if you want to get practice or try this one out, just to see how you do, you can just pause it right now and just try this one out. So we should get that the value is also 27 over 2. So then, of course, the natural question is that a coincidence that switching the order of integration got the same answer? And no, it's not a coincidence. This is actually a theorem that we can talk about right now. This is Fubini's theorem. Fubini's theorem says if f is continuous on the rectangle R with x from a to b, y from c to d, then the double integral over R is equal to, this is the double iterated integral of f of xy dy dx, and it's also equal to the double iterated integral of dx dy. So in other words, as long as we have a continuous function over a rectangle, the order of integration won't matter. Now, this only applies to rectangular regions. We have to be very careful because once we get into, say, like the next section and we're not working with just rectangles anymore, this property will not apply anymore. So it only works for rectangles, only works when you have constants like a, b, c, and d up in those bounds. But it can be a useful tool for us in these cases. So for this example, evaluate the double integral of x minus y, 3y squared dA, and we're given these bounds for x and y. So let's see, I will do the dx dy case. So x is going from 0 to 2, y is going from 1 to 2. So we'll evaluate this innermost integral here with respect to x. So that's going to be 1/2 x squared minus antiderivative of 3y squared with respect to x. 3y squared is all constant, so its antiderivative just picks up a factor of x. So it's like if you're taking the antiderivative of 5, the antiderivative would be 5x, something like that. So this will be 3xy squared. And all of that is going to get evaluated from 0 to 2. Okay, and the dy integral is still out there because we haven't taken it yet. So from here, we get integral 1 to 2. Let's see, in the case of the 2, we're going to get 4 over 2, which is 2, minus 6y squared. And in the case of the 0, we get 0 minus 0, so that ends up not playing a role here. And now we have single integral, single variable, so we can go ahead and just anti-differentiate, evaluated from 1 to 2. So 2, that's going to be 4 minus 16, minus the 1 case is just 2 minus 2. So we get negative 12. Now, up until this point, we've been talking about double integrals in terms of volumes because we have surfaces that are all above the xy plane. The fact that we got a negative here, that just means that this surface was not above the xy plane, or maybe part of it was and part of it wasn't. So this, we're not interpreting this necessarily as volume, but it would represent volume between the surface and the xy plane, both above and below. So the below gets counted negatively. So I would encourage you to try the other direction here. These ones are really good ones to practice just because we already know what the answer is supposed to be. So if you set up the dy dx case, y from 1 to 2, x from 0 to 2, you should also get negative 12. And again, we know that these should be the same answer because of Fubini's theorem. So Fubini's theorem says these should be equal. So feel free to give that one a try and see how you do. Make sure you can get to negative 12 as well. Now for this next example, one very effective use of Fubini's theorem is cases where solving with respect to one variable is actually easier or harder than the other. Because up until this point, right, we've had like this polynomial here. It didn't matter the order, right? We could have done x first, we could have done y first. You get the same thing, and it's about the same amount of work, right? Same level of work. But what if we have a function where it's not the same? These are cases where we actually do want to take Fubini's theorem into account. So this is given to us just in general terms, dA, and it's up to us to decide if we want to do it with respect to x or y first. If you notice, there is a y here and there's a y inside the sign. That means this is a product of functions of y. So integrating with respect to y right now is probably not a good idea. And I want to go ahead and just make a note of that here at the top. So if we do y first, so we would get double integral y sine of xy dy dx, y from 0 to pi, x from 1 to 2. This inside integral, having a product of functions of y like this, we would have to do integration by parts twice in order to actually solve out that inner integral before we could get to the x's. Now, this isn't to say that that's not possible, because we do know how to do integration by parts, but it's certainly not preferable if there is an easier way. Anytime you get a problem that requires multiple integrations by parts, we would probably hope to find a potentially simpler way to do it. So let's see what happens when we do it with respect to x first. So we got y sine of xy dx dy, with x going from 1 to 2, y going from 0 to pi. If we take the antiderivative of the sine, so the outer integral is still there, antiderivative of sine is negative cosine of xy. And when we take the antiderivative, so like if we were to take the derivative of this, like to go backwards, derivative would be sine of xy times y, because of the derivative of the inside, right? The chain rule, partial with respect to x of xy, would give us this extra factor of y, and that's right there. So when we are anti-differentiating, we're undoing these steps, the y gets taken out. Okay. Another way you could think about it is you could set up kind of like a u substitution here, just with partial derivatives instead of the full derivatives. But either way, by taking the antiderivative, that y, which was present from a chain rule, is able to go away. And this is going to help immensely because now we'll go ahead and sub in the x's. So integral 0 to pi of negative cosine of 2y minus negative, so plus cosine of y dy. Because now we have an integral with respect to y and no products anymore. It's just a sum, a cosine here, a cosine there, and that's it. So now if we take the antiderivative, antiderivative of negative cosine is negative sine. And because it was a 2y, in order to undo that step, we need to have a 1/2. So that's negative 1/2 sine of 2y, and then plus sine of y. And that's going to be evaluated from 0 to pi. So if we evaluate at pi, we get sine of 2 pi, which is 0, plus sine of pi, which is 0, minus sine of 0, which is 0, plus sine of 0, which is 0. So this whole thing just amounts to a big 0. So for this example, solving it with respect to x first was much easier than solving it with respect to y first. And so there are times, even though sometimes Fubini's theorem doesn't necessarily matter where, the order, we can just change it. It's not going to matter that much. Some cases, it does matter where you get problems like this, where doing it with respect to one variable first makes your solution that much simpler. Let's take a look at another example here. Find the volume of the solid S that is bounded by the elliptic paraboloid, given here, and the planes x equals 2 and y equals 2, and the 3 coordinate planes. So if we look at the solid S here, so S is under this surface here. So let me go ahead and solve this for z, just so we have that in its more functional form. So that's 16 minus x squared minus 2y squared. And above, we have the 3 coordinate planes. So that's x equals 0, y equals 0, z equals 0. And we're going up to x is 2 and y is 2. So we're above the square r with x going from 0 to 2 and y going from 0 to 2. And if this problem looks familiar, it's because this is the exact same problem that we were doing with the Riemann sums a little while ago. So where we approximated the volumes of the boxes, those 4 boxes above the surface, above this square but below the paraboloid. Now that we have the techniques of double integrals, we can find the volume not approximately, but exactly. So we can set up the double integral over r of 16 minus x squared minus 2y squared dA. Because it's Fubini's theorem, because it's a square or rectangle, we can pick the order of integration. It doesn't matter. There's not really an inherent easier way to do it this time. So we get 16 minus x squared minus 2y squared. So I'll do dx dy. And they both go from 0 to 2. So we'll take the inside integral with respect to x first. So that's going to be 16x minus 1/3 x cubed minus 2xy cubed from 0 to 2. Plug in the 2. We end up getting, so 32 minus 8 over 3 minus 4y cubed. Excuse me, not cubed, squared. So minus 2xy squared. So combine, give a common denominator to those first terms. We end up getting 88 over 3 minus 4y squared dy. So then we take the antiderivative with respect to y, so that's 88 over 3 times y minus 4/3 y cubed, evaluated from 0 to 2. The 0 case, again, turns into nothing. You shouldn't always assume that the 0 case turns into nothing, because there will be times when it doesn't. But in this case, it did happen to. And then the 2 case, multiply that in there. We end up with a final answer of 48. So the volume of that solid S that is below the elliptic paraboloid and above this square, the volume is 48. Now, if we look back at what we had gotten with our approximation the first time, we got that the volume was 34. And we mentioned that this was an underestimate, and it sure was. We were 14 units below the actual volume. That's over 25% less than the actual number. But again, we only used 4 boxes. So this was not bound to be a highly accurate approximation. But this one now is the exact value. This is the exact volume of that solid. Now, there's one more property to talk about here when we're talking about rectangular regions and Fubini's theorem and such. Consider the case where we have a function f of xy can be factored as a product of a function of x only and a function of y only. So as a product of a function of x only and a function of y only. Okay, so you have g of x times h of y over this rectangular region. Fubini's theorem gives us an interesting result that we can apply. So we have double integral over r of f of xy dA. So this is, I'll write this out as the iterated integral. The function will be g of x times h of y inside. So dx dy with x from a to b, y from c to d. Now this, go ahead and just put another copy of it over here. Just widen this out a little bit so that I can then put some brackets. because I want to kind of separate these a little bit. Okay, so these are the same thing. Haven't changed anything yet. With respect to this innermost integral, with respect to x, y is a constant in here, right? Not out here, but in here, in this one only, it is a constant, which means that this function h of y is also constant. So since y is constant with respect to x, h of y is constant. And there's a rule that we have from integration that constants can be pulled out in front of an integral. So that's exactly what we're going to do. We're going to pull it out. So we're going to pull h of y out, not of the whole thing, not the double, but just out of this inside one, the dx integral, because it is a constant with respect to x. So we're going to have integral from c to d of h of y times the integral from a to b of g of x dx, and then all with respect to y out there. Now, here's the kind of interesting part. If you consider this outer integral with respect to y now, this function right here, this is just a single integral in terms of a single variable now, right? Integral from a to b of g of x dx. Once this gets evaluated, it's going to turn into a number, right? Because you're going to take the antiderivative, you're going to plug in a and b and subtract. This is a number, right? So this is a constant. And not just with respect to y, but this will be just a number, a true constant for all values here. So what we can do with this constant is move it out to the front of this integral. So we're going to pull it out. And so we get integral from a to b of g of x dx times the integral from c to d of h of y dy. So it turns out, say thus, our double integral over r, when you have a product of functions of x times functions of y, you can actually split it into the product of two separate single integrals. And this is where the region R is rectangular. And again, this is a result of integration properties and Fubini's theorem. Fubini's theorem, of course, guaranteeing that it doesn't matter the order that these are in, this property will always hold. So it needs to be over a rectangle. Again, as soon as we switch away to non-rectangles, this property won't hold anymore. So this is not a catch-all for every double integral. But in these certain circumstances, this one can be very helpful because you're able to take a double and split it into two singles and then solve the singles separately. So it's basically just making it a Calc 1 problem, just twice. So, for example, evaluate double integral over r of sine of x cosine of y dA, with x and y both going from 0 to pi over 2. So we have double integral sine x cosine y. Doesn't really matter what order we put them in. dy dx, 0 to pi over 2, 0 to pi over 2. We have a function of x times a function of y. They are perfectly separable. So, and we have constant bounds, right? A rectangular region. So we can go ahead and split. So we'll get 0 to pi over 2 sine of x dx times integral 0 to pi over 2 cosine of y dy. We'll take the antiderivatives. So that's negative cosine x, 0 to pi over 2, times sine of y, 0 to pi over 2. Negative cosine of pi over 2, that's 0, minus negative, so plus cosine of 0, which is just 1. Sine of pi over 2 is 1, minus sine of 0 is 0. So we get 1 times 1. which is just 1. So the value of this double integral is 1. And of course, you could have done this using the traditional technique. This is just an additional tool to be able to help us solve some of these problems more efficiently. But you didn't have to use this property to do it. You could have done it directly using the same techniques we've been using this whole section. Now, the last thing to look at here, we've got a short list of a few properties of double integrals. The properties of double integrals are very similar to those of single integrals, so these should look familiar. If you have a double integral of a sum of functions, f plus g, you can split it into the double integral of f plus the double integral of g. Okay, this is not the same thing as this property up here. In this property, the double integral of g times h split as a product of two single integrals. This is just a regular integration technique where you're splitting it, but you're still keeping them both doubles. So you're basically just moving the functions apart from each other and then evaluating their double integrals separately. Okay, so this is not the same thing as this one. This one is a special case up here. If you have a constant inside a double integral, it can come out of both integrals. And if you have one function that is greater than or equal to another for all x and y, then the integral of that function will also be larger than the integral of the other. So if one function is above another one, the volume beneath it will also be larger than the volume beneath the smaller one. Okay, so hopefully kind of mentally that tracks with everybody. But that brings us to the end of section 15.1. That is our introduction into double integrals over rectangular regions. When we come back in the upcoming sections, we're going to be looking at what happens when the region is no longer rectangular. How do we handle the double integrals then? And we'll look at some additional uses and different kind of variations on this integration technique. So I will talk to you all very soon in those upcoming sections.